So today we're going to look at inverse trigonometric derivatives. And this is actually the other and probably even more useful application of the rule that we introduced last time with the derivatives of inverse functions. So if you remember correctly, if g of x is equal to the inverse function of f, then we know that g prime of x is going to be 1 over f prime of g of x. That was the rule that we introduced last time. So we're going to actually use this rule to derive what the formula would be for the derivative of inverse trig functions. And the one that we're going to look at today is the inverse sine. We can actually do a very similar process with all 6 inverse trig functions, but we're going to do the proof for the inverse sine function. And what we want to do is we want to find the derivative of this. Okay. Now, again, the inverse sine function, sometimes this is known as the arc sine function. Again, this is not the same thing as cosecant. So sine inverse of x is not the same thing as 1 over sine of x. Instead, what it is it's going to be a function where if y is equal to sine of x, then x being equal to sine of y, basically this is going to be the inverse function is going to be the thing that satisfies this equation here. And then there, of course, are domain restrictions on what the value of the output of sine it has to be in that particular case. So let's think about how we would do this then if we apply this formula. Well, f of x, of course, is going to be equal to sine of x. And if I want to find g prime of x, well, what I need to do is I need to have 1 over f prime of g of x. So that means that g prime of x is going to be 1 over, so f prime of x is going to be equal to the cosine of x. So we're going to say that this is 1 over the cosine of, and then g of x is going to be the sine inverse of x. And you might say, well, how is that helpful? This looks like it's confusing, but actually it turns out that this denominator can be simplified. If you remember, the way that trig functions work is if I take the sine of an angle, remember that that's going to give me the opposite over the hypotenuse. I know that the cosine of an angle is going to give me the adjacent over the hypotenuse. And then the way that the inverse trig function works is that if I take the sine inverse of some sort of opposite over hypotenuse, I'm going to get out an angle. And likewise, if I take a cosine inverse of some adjacent over a hypotenuse, that will also give me an angle. So the way we simplify this denominator is that we're going to want to think about this geometrically speaking. So we're starting with the sine inverse of something that's x, and the sine inverse, the input, is going to be some trig ratio opposite over hypotenuse. That will give us some angle. So this right here is going to be some angle. And then once we take the cosine of that angle, that's going to give us some adjacent over a hypotenuse there. So what we do is we draw a picture. It's called an auxiliary triangle. And if I assume that this is the angle here, we've got our 3 sides. We have basically our opposite side here. We've got an adjacent side here. And we've got a hypotenuse side there. Since we know that we're taking the sine inverse of an opposite over hypotenuse, we're going to let the opposite be x, because this is going to be x. And implicitly, we can think about this as being x over 1. A hypotenuse would have to be 1 in order for the ratio to be x over 1. That, of course, will give us some angle. We don't know what that angle is, but we don't need to know what that angle is, because once we take the cosine of that angle, we'll be left with the adjacent over the hypotenuse. So we just now need to figure out what the adjacent is here. And since this is going to be a right triangle, we can use the Pythagorean theorem to deduce that this is going to be 1 minus x squared. Okay? So that means that the cosine is going to be, of whatever this thing is going to be the adjacent over the hypotenuse, which is just going to be the square root of 1 minus x squared over 1. So it turns out that this entire thing actually simplifies to be 1 over the square root of 1 minus x squared. So even though we're taking the derivative of an inverse trig function, the surprise thing is that we actually get some sort of algebraic expression without any sines and cosines in this. So this is actually the derivative of the inverse sine. And in a very similar vein, we can actually find the inverse trig functions of the other six inverse trig functions. Of course, we just found sine inverse, and we found that was the derivative. That was 1 over 1 minus x squared. We can do a similar construction with inverse cosine to show that we get negative 1 over the square root of 1 minus x squared for the derivative of inverse cosine, and then 1 over x squared plus 1 for the derivative of inverse tangent. And these are the ones that are most common that you're going to see. Every now and again you might see the other three, but these are very rarely used, and I'm going to simply put these here for your reference in case you do use them in your class. But in my personal practice, I don't think I've ever used these formulas in any type of math setting, so just make sure that you know these three, and that should be sufficient for most of your math experience. Now, once we have these formulas, we can do examples. So let's say I want to find the derivative of the tangent inverse of x squared plus 2x minus 1. And of course, we remember from the last slide that the inverse derivative of the inverse tangent is going to be 1 over x squared plus 1. So to find the derivative of the inverse tangent of this thing here, what we need to do is use the chain rule. So remember, the idea here is that we're going to take the derivative of inverse tangent. So that's going to be 1 over, and then instead of an x here, we're actually going to plug in what was in for that x. Again, it looks a little bit funky here. And then we're going to take the derivative of whatever that stuff is. So whatever the derivative of, x squared plus 2x minus 1. So this is going to be just 1 over, and then we're going to plug in x squared plus 2x minus 1 squared plus 1 times, and we can actually put this in the numerator. That's actually going to be a lot simpler. The derivative of x squared plus 2x minus 1, which is just going to be 2x plus 2. So this is going to be the derivative of this example up here. Again, as always, I hope that you found this video helpful, and as always, take care.